All right, cool. So we can get started. Hopefully, so everyone in the room can hear me. Our audio setup is kind of weird because we did it ourselves. So, and you can double check live stream can hear us. Okay, cool. Welcome to the first FireSim and Chipyard user and developer workshop. We're super excited to be hosting this. We have lots of great speakers today. We're going to be talking about all their cool projects. It's 9:10, so we'll get started. Again, the program is on the FireSim website. And there's also a Slack where remote attendees, if you're on the live stream, can ask questions and we'll repeat them to the presenters as they at the end of their talks. Okay, so just a quick intro. So why are we here? Well, we're in this golden age in computer architecture research. We've lost a lot of traditional scaling techniques, but as an architect, this is sort of the dream world, right? Everyone now wants custom microarchitectures and these hardware software co-design systems. And it's also a great time to have direct impact as researchers, right? There's this exploding open source hardware movement and an open ISA, RISC-V, that can run software that is interesting, that we care about, and substantial. But for a long time, we were sort of in this dark age of computer architecture tools. And if you think about what we need to do good architecture research, especially in small teams, right? We need tools that let us evaluate designs on all these metrics. It has to work, of course, but then power, performance, area, and things like frequency. And especially in small teams, these tools need to be agile, right? And historically, we didn't even have good open IP. And so we had to do things like build abstract architecture, microarchitecture simulators, because we really had no other choice. It was impossible for one person to build up the whole RTL world to do interesting research. But now, luckily, we have much better IP and software compatibility for that hardware IP. So what's stopping us? Well, if we look at the tools that are classically used, right, they're designed to be operated by hundreds of engineers rather than a few grad students or a few engineers in a startup. And there are essentially three hard questions that arise out of trying to fix these tools, right? So the first is, where can I get a collection of IP that actually works together and has software stacks that run on top of it? Then once we have that sort of complicated system that we've built up, we now need to evaluate it. And there are two ways we want to evaluate it. Of course, we want performance measurements. Just think, how much time does it take to run my workload for this novel system? But then we also want to get ASIC QR feedback like area and frequency, and maybe even tape out a design so that we can understand whether it's realizable or not. And so I will posit to you that we've answered these three hard questions with the tools we'll talk about today and that the speakers will also talk about today. So where are we going to get a collection of well-tested hardware IP? That's Chipyard. How are we going to quickly obtain performance measurements for the systems we build? That's FireSim. And then how are we going to get ASIC QR feedback for our designs? And that's Hammer. So put together, we'll be able to do all of the things we want to do, right? We can make sure our design works, but then measure power, performance, area, frequency for these complex systems that we're building up with a few engineers or a few grad students. So for folks that are new, I'll do a quick overview of what Chipyard and FireSim are, and then we'll move on to the actual talks. So what is Chipyard? Chipyard is essentially this organized framework that is composed of various SoC design tools. It's also this curated library of various open source RISC-V SoC construction components, and it's a methodology for doing agile SoC architecture design. So you'll see that in this diagram on the right-hand side, there are kind of a few different kinds of things. There are a bunch of RTL generators sitting over here that can generate all of the parts of an SoC that you might want. Then there's a flow for taking these RTL generators and their output and converting it to the various evaluation and build methodologies that we might be interested in. So we can do fast simulation, software simulation, FPGA prototyping, as well as push it through a CAD flow to get ASIC QR information. So as a quick overview, I'm doing sort of an overview of an overview. So I have screenshots of other people's overview slides here. So what's in Chipyard? A bunch of different cores, right? There's things like Rocket and Boom, Pulp cores from ETH, Sodor educational cores that we use in courses, and a new feature in the latest Chipyard release called Spike as a Tile, which lets you plug in an ISA simulator when you need to, for example, do faster simulations. There are a variety of different accelerator sockets. These are the ones that are open source so far. Rock accelerators let you have this sort of closely coupled accelerator sitting right next to the CPU that has access to the top side of the L2 or the L1. and can receive RISC-V instructions and respond directly to the core. Then we also have MMIO style accelerators. These are kind of accelerators that sit on the NOC inside of the system and look more like kind of classical accelerators you might be familiar with. And then there are a bunch of other sorts of sockets that people have experimented with in both user work, things that will become upstream in the coming months, things like modeling PCIe and so on. There's also a lot of interconnect IP inside Chipyard. So there's a whole coherent interconnect that can be constructed based on the tie-link standard. And there's all of the IP you need to actually construct these sorts of complicated systems. A relatively new feature in Chipyard is the Constellation NOC generator, which is a parameterized chisel generator for essentially arbitrary SoC interconnects. And you can see a diagram of a sort of system, looks much more like a real modern system than kind of the classic interconnect mechanisms in Chipyard. So you can build complicated NOCs with complicated topologies very easily and productively in Chipyard. Some more IP, this is not interconnect IP, but L2 and DRAM. So we have an open source tie-link L2 that was developed by Sci5, integrated into Chipyard, very well verified, fairly rock solid. And we have DRAM interfaces to external controllers. And when we talk about FireSim later, also models for doing fast modeling of DRAM on things like FPGAs. There are also a bunch of different peripherals. We have things like JTAG, debug modules, and then more classical stuff that you need to interact with your system. Things like UART or GPIOs, SPI, etc. And just to give you a sense of the kind of complexity of systems you can build in Chipyard, here's an example that attendees at our tutorial yesterday actually ran simulation for live in the tutorial. So this is a pretty complicated system with 28 coherent cores interconnected with a NOC built with Constellation. You can see there's some complicated out-of-order cores here, some in-order cores here, some accelerators, all kinds of good stuff. So this is the kind of system that you can compose very easily inside of Chipyard. So just to summarize some of the flows, what you can do with the designs you build in Chipyard, you can of course do software RTL simulation, push it through tools like Verilator, Xcelium, or VCS. You can push it through a VLSI flow called Hammer that I mentioned earlier. And the sort of notable thing here is that this is designed to be portable across different processes and different tools. Then there's FireSim, which I'll skip for now because we'll talk about it in depth in a little bit. And then there's FPGA prototyping if your final deployment target is an FPGA, because you're actually going to deploy an FPGA in the wild, or as a bring-up platform for taped-out chips. So there's a bunch of community growth around Chipyard, as you will see in the talks today. We've put up lots of documentation, and there's a mailing list that's fairly active with folks asking questions and getting responses from the community. Of course, all of this is because everything is open source on GitHub. And of course, we welcome issues, feature requests, PRs, and all of that sort of good stuff. Some interesting stuff on the education side in Chipyard. Chipyard is used pretty heavily in Berkeley's architecture courses. So a bunch of different courses here at Berkeley have used Chipyard in various fashions. You can see in this diagram here. And there's a really nice advantage to having this common and shared hardware framework across these classes, right? It reduces the ramp up time for students. Once they take sort of one of these classes and get used to the infrastructure, they don't have to learn a new thing every time. And as a result, they can be far more productive in the later classes that they take instead of relearning frameworks over and over. And as a result, this enables more advanced course projects like taping out a chip in one semester. So this was an article from, I think, few years ago now. Basically, Berkeley engineering undergraduate students pull off novel chip design in a single semester. So these are undergrads who have no chip development experience. We're able to take Chipyard, push it through Chipyard's VLSI flows, and actually tape out a chip. The chip came back and actually works. So this is the kind of cool stuff you can do in Chipyard. Okay, real quick. So what is FireSim? So at a very high level, FireSim is designed to let you do pre-silicon verification and performance validation of your design. So of course, taping out a chip is really great, but we want to make sure that what we're building makes sense before we go tape out a chip. And that's sort of where FireSim fits in. We want to do that as fast as possible, so much, much faster than software RTL simulation. But we want to get some of the advantages that software RTL simulation has versus just dropping stuff on an FPGA. So what FireSim is going to ingest is some RTL design, right? That's going to be either Fertile generated by Chisel or maybe black box Verilog, or of course all the Chipyard generated designs I showed you on the previous few slides. Then it's also going to ingest hardware or software I/O models, and I'll talk about why we do that in a second, as well as workload descriptions for complicated Linux software stacks so you can automatically boot on top of these systems. And so once you do this, we're essentially going to produce this fast cycle exact simulation of the design and the whole world around it. And we can automatically deploy this both on-premises FPGAs and cloud FPGAs. So things like Xilinx Alveo cards or EC2F1. So at a very high level, where does this fit in within an architect or chip developer's toolkit? Well, of course, you're going to do a high-level simulation before you start writing any code or any RTL code to understand whether your design makes sense. But then you're going to write some RTL in software. You're going to co-design that in software RTL simulation. And then traditionally, at least in academia, you might do an FPGA prototype here and then tape out the design. And we'll talk about some of the pitfalls of FPGA prototypes in a second. But what was really missing here was this ability to do co-design and FPGA accelerated simulation. And that's where FireSim fits in here. So we can take our design, boot an OS on it, run an entire software stack that's complicated that runs for a long time, and we can get realistic performance measurements from this before we, of course, tape out a chip and then get a chip back. So what about FPGA prototyping? So there are several pitfalls with FPGA prototyping, and I think this example kind of tells it in a very simple way. So let's say we have some SoC that we want to build. We're eventually going to tape out that SoC. We've written a bunch of RTL for it. If we taped it out, let's say it runs at 1 gigahertz, right? And that SoC is going to be attached to some real-world DRAM that, say, for the sake of argument, has 100 nanoseconds of latency, right? So in this real system, the SoC is going to see 100 cycles of DRAM latency. Right, but if we build an FPGA prototype of this thing, right, just take that RTL and put it on the FPGA, connect it up to the FPGA resources. One problem is going to be that your RTL is going to run at something like 100 megahertz, but it's still going to be talking to that real world DRAM with 100 nanoseconds of latency that's attached to the FPGA. So if you run software on this thing, you're going to get incorrect performance from the memory system by a factor of 10, because the SoC is now just going to see 10 cycles of DRAM latency. So this brings us to essentially what are the distinguishing features of FireSim. So again, we're not building FPGA prototypes. We're going to build FPGA accelerated simulators. And unfortunately, I don't have time to go into the details in this talk, but essentially what's going to happen is we're going to automatically transform RTL designs into these simulators via something called host decoupling. And doing this will also enable a bunch of new debugging, resource optimization, and profiling capabilities. The other nice thing is that we'll be able to flexibly scale from on-premises FPGAs to cloud FPGAs. And having standardized host platforms both in the cloud and locally makes it very easy to collaborate with other researchers and do things like artifact evaluation. So lots of papers now that have used FireSim have gone through artifact evaluation using both local and cloud FPGAs to let other reviewers review that their project works using FireSim. And so the way this is possible is because there's lots of automation inside FireSim to hide the FPGA complexity, regardless of whether you're running on-prem or on the cloud. And of course, all of this is open source, so you can try it out yourself. So why do we need host decoupling? Well, because FireSim has host decoupling, we get a lot of nice features that FPGA prototypes don't have, right? Our simulations are going to become deterministic, which is not usually true with FPGA prototypes. We're going to get identical results as we move across different types of host systems, different FPGA vendors, and so on. Also not usually the case with FPGA prototypes. And decoupling will also give us support for a bunch of nice features, as I mentioned earlier. We're going to get software co-simulation. So we can have parts of our system running in software and the host machine attached to the FPGA, and parts of it actually running fast on the FPGA. So we can offload things that are not so important into software. We can simulate very large targets over distributed hosts, and I'll talk about that in a second. We can also do a lot of non-invasive debugging and instrumentation. We had papers on this at past ASPLOS, and there's one this time too from one of the folks in our lab. And we can do all sorts of cool multi-cycle resource optimizations that let us pack more stuff onto the FPGA, making trade-offs between simulation performance and FPGA capacity. All right, so more broadly, what can we do with FireSim? So the sort of simplest use case is just doing classical performance measurement, right? So let's say we have some processor, we made some architectural improvements to it, and we want to run spec int 2017 on this thing with complete reference input, so we don't have to do any sampling or anything like that. Now with FireSim, we can do this on 10 FPGAs in parallel running on the cloud, each simulation running at over 150 megahertz. We can run this entire suite on our novel design within a day. And this was done in the original phased paper as sort of a test case and validation for the memory model inside FireSim. Then there's all sorts of other design space exploration you can do because we can very easily on the cloud spam out lots of Vivado builds, bitstream builds for designs, and we can very easily sweep parameter values in Chisel. A bunch of other use cases across security, tons and tons of accelerators have been evaluated using FireSim. And there are also some nice debugging features in FireSim. We unfortunately don't have too much time to go into them here, but you can check out the FireSim docs. There's this whole index page. Each of these links points to some information about a debugging feature in FireSim. So this really lets you understand what's happening inside your design running on the FPGA, which is traditionally very hard with something like an FPGA prototype. We can also extend this to profile systems at FPGA speeds. So we can use that same sort of ability to stop the whole simulation world on the FPGA to get out-of-band performance profiling information on systems. Very quickly, I'll show you sort of what FireSim was originally built for, which is not just doing these kind of 150 megahertz single SoC simulations, but scaling out to simulate a whole data center. So here's an example of the kind of single node simulation you would run in FireSim, right? We have some Chipyard generated SoC. Again, we've done host decoupling here. So this sits in a little island on the FPGA, and it has a bunch of models, also synthesizable FPGA models, sitting on the FPGA fabric, right? So that DRAM model is sitting here is going to solve that problem I showed you earlier with FPGA prototypes not having correct performance for DRAM, right? There's a model sitting here that's going to present correct timing performance to the rest of your design, where capacity is still provided by the physical DRAM attached to the FPGA. So when your design makes a request to the memory system, it first goes through this DRAM timing model sitting on the FPGA. That model will make requests for any data needed to satisfy that request. And then at the correct time, according to the model, it will pass back a response to the rest of the system. And similarly, we can add other sorts of IO models for the rest of the IOs you might be interested in. So this is an example of a single server modeled in FireSim, right? We can run this at about 150 megahertz. And if we add networking simulation, which is what we need to model something like a data center, that goes down to about 40 megahertz, but we can talk about that out of band, why those costs are there. But in the original FireSim work, unfortunately don't have time to go in detail here, but we can scale essentially from this single design, taking up a quarter of an FPGA, onto 4 designs on a whole FPGA, onto 32 designs across an F116X large instance on EC2. Then we can just scale out on EC2 to get 256 nodes and 1,024. So what's really happening here is that we have this globally coordinated and synchronized simulation of 1,000 nodes running on EC2 F1 that's harnessing millions of dollars of FPGAs that we would never be able to afford for real to purchase in academia. We can run these large-scale simulations with cycle-exact modeling of all of the SoCs and this cycle-accurate network simulation with global synchronization, connecting them all together at a cost of only hundreds of dollars per hour to us. So we can scale out from these very small systems all the way up to these large 1,000-node systems. So what this essentially turned into then after that original work was a tool for just doing productive open source FPGA simulation, right? So if you can simulate 1,000 nodes, you can simulate 1 node for general SoC sorts of projects. So FireSim was open source, it's BSD licensed, and like I said, it essentially turned into this easy button for fast FPGA accelerated simulation. Everything is abstracted behind this FireSim command line program. So if you're familiar with Docker or Vagrant, it's basically like that, but for FPGA simulators. And a nice thing here is that scripts can call this to completely automate the process of distributed FPGA simulation. And so back in the original ISCA paper, we had a script before there was artifact evaluation in conferences that would reproduce the entire set of plots in the paper. And for a long time, this was actually kind of the release CI for FireSim before we shipped a new release, was to run this script and make sure we could reproduce everything in the paper. And as I mentioned earlier, now that conferences have artifact evaluation, a bunch of papers, some of which you'll hear about today, have gone through artifact evaluation using FireSim. There's a bunch of documentation, and if you're an academic researcher in particular, you can get grants for both AWS and donations of Xilinx FPGAs. And so, of course, for a long time, FireSim was cloud only. Now there's support for on-premises FPGAs. And we sort of extended all of the automation that was present in the manager for doing on-cloud stuff to on-prem FPGAs. And we have a bunch of documentation now in FireSim docs that lets you very easily go from a bunch of parts sitting on your desk to a complete system that can run simulations with an FPGA attached. And the nice thing is that all of the existing FireSim features work at scale and locally. So we'll talk more about the community as we go through today, but just to give you a sense of all the projects using FireSim, at this point, there are more than 200 mailing list members and over 800 cloners, unique cloners per week. There's tons of open source projects with public FireSim support. We can't list all of them here. Also, a few companies have publicly announced using FireSim, and you'll hear from some of them today. Also, tons of papers have used FireSim. You'll also hear from some of these folks today. But this is just a short list. There's over 20 additional papers on the FireSim website that have used FireSim at this point. And in total, FireSim has been used now in published work from authors at over 20 academic and industrial institutions. And so this is actually used in the paper for some evaluation purpose, not just the paper was cited. If you're new to FireSim or Chipyard, you unfortunately just missed the tutorial yesterday, but we'll be uploading all of the stuff from our tutorial yesterday onto the website that you see here. All the slides are already available, but probably tomorrow we'll post videos that we recorded from all the sessions and all the getting started scripts if you want to try it for yourself on your own EC2 instances. Okay, so with that, we will get started with the keynote. So please bear with us for 1 second as we swap in the presenter.